So with us, who is currently working as an assistant professor in Indian Institute of Technology, Delhi, in the Center for Automotive Research and Tribology, which is abbreviated as CART. His main research interests include thermal designs of battery packs, lithium-ion battery state estimation, energy storage systems, recycling of battery packs for electric vehicles, intelligent optimization for engineering design, etc. He's completed his PhD and have done a postdoctorate from NTU Singapore in the year 2015. He was also awarded the Best Paper Award from the Journal of Frontiers of Mechanical Engineering in the year 2018. He has been awarded Guangdong High Level Provincial Talent Project. Besides, he has been the principal investigator of academic and industry projects sponsored by State Key Laboratory of Digital Manufacturing, that is under Ministry of Education of Guangdong Province of Provincial Scientific Research Fund from 2016 to 18. Besides, he has also been involved in many projects as a principal as well as co-principal investigator, and has many publications of high impact factor to his credit. So with that introduction, I welcome Dr. Ahkil, and the stage is all yours now.
Thank you, Professor Amit, for the kind introduction. And I will first of all like to thank you and your team for organizing this wonderful FTP program, where we have a very nice online platform and got chance to interact with the faculty, students, researchers. So this is quite a good platform, and hopefully I'll be able to share about my upcoming, about my ongoing and my past research on batteries, and also share some opportunities for students, and of course. So thank you very much, and for your wonderful this program. So I'd like to share of my screen about today's topic. So is it visible now?
Yes.
Yes, it's visible, right? Okay.
Right.
Okay. So today I will share about what kind of work we have done in battery module case for electric vehicles, with emphasis on monitoring, safety, and recycling. I'm sure that the previous lectures have been focused on fuel cells, cell modeling, battery modeling. So now after this, we have moved to the battery module levels. Okay, this is more like a stack level case. So what kind of focus on this trick? Battery module or battery pack, where we have individual batteries or the cells, and these are configured in series as well as the parallel. So we have been focused on SOH, estimation of the cell level, material characterization, of course, it includes, and also we are also have been focusing on how we can assemble these cells together in an intelligent way or an optimal way to form a battery pack. And also we have been focused on the cooling mechanism, which can be air cooling or the liquid cooling. And in addition, we have also been focused on the pack design. So where we are actually considering more mechanical sort of analysis, such as deformation analysis or static or the frequency response analysis. So these are all kind of a brief overview of our focus. In terms of research directions, objectives, and our results, I will go through some few of the topics, such as 5 topics, which are mainly emphasized on battery module. So this include performance, safety, recycling, monitoring, so all these aspects. So when we design our battery module, we have to be very sure how we configure the cells together in series and parallel, and what is the optimal spacing between the cells. In second case, how we design the cooling system, for example, air cooling or liquid cooling. And in the third case, how we can reuse the existing battery modules to form our new modules, and how we can control the battery module states using AI. And also the last one is the mechanical design aspect. So these are some research directions. I'm going to go in very brief. I'm not going to go in very in depth, so which you can actually read from my papers. So just give an overview of what actually is all about these directions. So first of all, I'm going to discuss about design of battery module with uniformity and equalization criteria for batteries. So as you can see, this is the battery module, which I've shown in this picture. So this comprises of cells which are in series as well as in parallel configuration. And there is a BMS also, which actually regulates the battery temperature, voltage, current, and other aspects. So what is actually the problem in this kind of design is that usually these battery modules are actually manufactured in large quantity, mass production. So most of the time what happens is that so these cells are actually combined in more or less in a random way. So what happens when these cells are manufactured in large numbers? Obviously there is a lot of no uniformity, or there is these cells do not have the equal or the same characteristics. There will be some difference or variance in characteristics among these cells. So this can actually, what can do is that this can actually lead to uneven temperature distribution, uneven charge and discharge profiles when we use this battery pack in real time, and this can actually degrade the lifespan of the battery. Okay, so this is why this sort of inconsistency among the cells in the pack can be very dangerous, can decrease the overall life cycle and the energy density of the battery pack. So for example, I can give you one example also. So we can see that in this table, we show you the single cell and the module for different EV batteries for BMW, LEF, and Tesla. So you can see that single cell energy density in case of BMW is 140 watt hour per kilogram. In case of battery module is 110. So there is a reduction of 33%. Similarly, in case of LEF, and similarly in case of Tesla. So the reason behind this is the inconsistency in the cells production. Even though when we visit the industry, we can see that they have a large production of cells, and also they have to do sorting, packaging, and they have to deliver the customers in time. So this can lead to the quality control in the cell production industry is not very good. So even though, and there is one very good problem which in industry they even ask us, like, how do we identify the good and the bad cells in the production line? I mean, during the production line, how do we identify the good and the bad cell without doing the necessary testing? So this is also one of the industry problem which is still on research. Maybe they will try to use some non-destructive techniques or image processing or some kind of AI-based systems has to be developed for that to ensure the quality control in the production line of the cells. So we did a small experiment to design some small packs, for example 3x4P packs, so where we can actually these packs will be actually designed based on the cells having the similar performance. Okay, so we did this a very basic experiment where we have 5 packs, A, B, C, D, E. A pack will be from the market, and B, C, D, E, these are the 4 packs. What we did is we disassemble them and we recover the cells. As I mentioned, 3x4 means 12 cells. So we recover the cells from current, temperature, and capacity. So we actually apply the clustering analysis based on the data we have collected. So this clustering analysis is a machine learning tool which can provide us a cluster which these cells have same performance. For example, maybe cell 1, 2, here cell 13 and 14, and cell 30, 31 can have similar performance. Okay, so this can provide us a cluster. So these cells have the similar performance. So then we can design those packs again from this combination of cells in these 4 packs, and then we can compare and validate with our external market, the pack we buy from the manufacturer or from the market. So this is a small experiment we did, and to do this experiment, we purchased the necessary machines. We use the Newware machines, And to do the testing, like the testing of the parameters, we did for 20 cycles initially, and we recorded voltage, capacity, temperature, resistance. Okay, so we use Newware machine and the data acquisition system and all these things. And so how do we disassemble them? So as I mentioned that we have 4 packs, 3x4P, and this is the lithium and battery pack. So you can see here, this is a small BMS controller, and we try to dismantle this very safely and recover 48 cells from here. And we did all this testing of 20 cycles on this the testing system. Okay, so this is all the overview process of our disassemble and the testing process. So initial testing process to get the data. So how to do the testing? We use the CCCV, very basic pattern. So we use the value of 1.3 ampere and cutoff voltage by 2.75, constant current discharge and constant current voltage charging. So we use this process for measuring the parameters. And what's the cell number and the capacity? We recorded this this graph so that you can see here very clearly. You can see here there is a variations among the cells. So you can see the cell number 1, cell number 2, 3. So minimum, maximum, and the average. There is a lot of variations between the cells for the capacity as well as the temperature. So similar case also happened for the temperature and also for the voltage and the current. So this clearly prove our hypothesis that there is a lot of variation among the cells. So what we did from this graph, we have this data already. So what we did, we apply the self-organization map. This is actually a machine learning algorithm for clustering. So we have clustering parameters such as capacity, voltage, resistance, and temperature. And we also have the clustering settings, 80% training, 10% testing, and 10% validation. Okay, so these are all the necessary parameters for the machine learning algorithm. And the what results we have achieved from there? So we have actually achieved the results of for 4 clusters. So we can make 4 clusters. So this is a cluster 1 where we have cell 1, 2, 3, 4. This suggests that these are similar performance. And then cluster 2. Similarly, in cluster 2 we have three groups. In cluster 3 we have 4 groups. In cluster 4 we have 5 groups. So actually we can divide this all 48 number into various groups and so first cluster have 2 groups, second have 3 groups. So we have to select that group, that cluster and that group where we can have all 12 cells and quite uniformly or quite spread distributed. So in this case we selected the 4th cluster and the 4th group. So this is the cell number 17, 19, 21, 26, 32, 33, 36, 40, 41, 42. So these are all the cell numbers. So what we are trying to do is that we are going to club these cells together and form our new pack. So what we do to form the new pack, we need a lithium ion battery welding machine. Okay, and we need a nickel plate. So we buy these holders from the market, and we can club this together, which 79 thing we did together. So this is how we can form our own pack. So we form pack 1, pack 2, pack 3, 3 different packs we form. Okay, so you can see here battery pack from the market, and this is the battery pack we form using our own approach. Okay, so this approach where we get this battery pack is from these clusters. Okay, so so now the question is, how do we test and validate these packs? Okay, because these are 3x4 and the voltage is around 12.5, 12.6. So for that one, we need a battery pack tester where we have the voltage rating, which can take up to voltage rating more than 12.6. Okay, and also higher current range. So this is why we purchased the Newware one and also the RB, both of them. And we did the testing, charge and discharge cycle simple test, and we recorded the capacity of our 3 packs. So you can see pack 1, pack 2, and pack 3 here, the capacity. Okay. Similarly, here also we recorded the temperature. We measure the temperature. So how do we measure the temperature? Actually, we keep the temperature sensor along the four corners of this pack and in the middle. Okay. So we use the thermocouples from along the 4 sides and also in the middle, and we recorded the mean value. Okay, so we try to see if we try to find the pack which recorded the minimum value of temperature, minimum value of mean temperature, and also the highest value of capacity. Okay, so in this case, we find that the market, the pack we buy from, we make our own pack. That one recorded a higher capacity and the lower value of temperature. Okay, so you can see here in this case that 28.83 is the lower temperature we have achieved, and also the capacity was a little bit higher. So this can give a very good idea or suggestion that there can be an improvement made if we can design the pack with the optimal in series and parallel. Let's say 10s, 1220p, or 30s, 40p, so something like that, a very large module. So yes, we can do that, but this process which we have done is a little bit time consuming because we have to disassemble, we have to measure the voltage, current, capacity, and then we have to configure the cells, cluster the cells. So we have to think about how we can do this part quite efficiently and quite effectively in a timely manner. So this part is still we have to do, and so these were the conclusions from our basic results, that our capacity of our pack was found to be higher than the other packs, and the maximum value of temperature at 6 different positions are smaller than the pack 1 and 2. Okay, so these were some of the results we got from our solutions. So, but a lot of work needs to be done in this case also. We want to go for the higher pack, okay, rear packs which are used in EVs, which is up to 72 volt and 48 volt. So that is also one question mark. And there are other techniques also, such as active balancing, passive balancing are there already, where actually we can provide the uniformity in the packs by activating the active and passive balancing techniques, where charge distribution or charge sharing is also there. So that is done through BMS. But this part is alternative technique, where before the operation, actually this is before the operation, how do we design the pack? Okay, this is a pre-operation phase, but during the operation phase, there is active and passive balancing techniques which are implemented in BMS. So now I will go through the second aspect, which is the cooling system design for thermal management. So this is actually a very important problem, especially in Indian perspective or other country perspective. This is very important problem because a lot of countries we have seen there is a fire catching in Tesla batteries, BYD in China, and other cases also. So why this is happening? First of all, the question is why this all thermal management is important and why this fire is happening. So as you can, I made a very small picture graph here where I have shown that you can see that temperature and the voltage is a graph, two axes, where you can see the lithium ion safety window. Okay, so this green portion actually it signifies that illustrate that this is a safety portion of the where the lithium ion battery operates very safely. Okay, so this is where it operates very safely. But other than that, if you go the voltage beyond this green range, or if you go the voltage below this green range and temperature, then there will be a lot of problems. Okay, like exothermic breakdown of electrolyte, thermal runaway will occur at very high temperatures. Okay, so breakdown of SCI layer, temperature rise, so lot of problems come. So maintaining the temperature and the voltage in this green range is very important. But ideal case, there is a necessity of cooling design. So that is why we need to design cooling systems, because this kind of thing we are not able to achieve. Okay, so so that's why in cooling system design, what we have do is that we have either we can use air cooling, okay, or we can use the liquid cooling. So there are other ways. So usually we try, so this is a small picture from one of my experiments which we did before. So we have 3x4 pack here. You can see the cooling fan is here, and we try to supply the cooling from the sides. Okay, and we try to record the temperature. Okay, so we do this experiment without
please
cooling.
Go on presentation mode.
Yeah. Okay. Once. This mouse is. I think, wait 1 second, the mouse is, I think it's not working. One. Yeah, now it's okay, right? Hello. Yeah. So
now it is okay.
Yeah. Okay. Fine. So actually, we try to do such kind of cooling system and study the effect of cooling fan placement. How do we place the fan, temperature, airflow rate? So these are all investigated. Okay. So this is the overview of our. This is the overview of problem and how do we try to address the problem on 3S 4P, the small packs. Okay. And also the influence of battery cell arrangement, the separation between the border and the cell. Vertical separation between the cell, horizontal separation is also investigated. So these are all some, parameters which need to be optimized so that we can get a very uniform temperature range in the batteries and uniform heat distribution. So in our case, we say this, we consider this as battery thermal management system. We say this BTMS. So we did actually for BTMS, we did air cooling BTMS, also the liquid cooling BTMS. So air cooling BTMS is considered the most inexpensive way because we just use the atmospheric air for this purpose. And liquid cooling is considered a bit expensive because we have to use active pump or we have to use active and passive cooling. So, but in case if we consider that we have very high discharge rates, and then we may go for liquid cooling. If we have to use inexpensive system and low discharge rate, then we go for the liquid cooling, air cooling. So there is also other one, PCM based BTMS, where we use phase change materials. Okay, so others one is also combination. So where we have intermediate cooling, where air and liquid or air and phase change materials. So this is all about batteries. So batteries can undergo a lot of abuse, penetration, overcharge, internal short circuit. So these are all unexpected and incidents that can happen to the battery. So therefore, cooling system and the thermal design is quite essential. So in our research, we try to focus on the application, development and application of surrogate models to solve the battery thermal design problems in EV. So surrogate models we can design using the response surface, radial basis function, or region. So cooling and cooling. We design optimization based on surrogate thermal modeling and parametric optimization. And liquid cooling also we do the similar part, but liquid cooling we have more objectives compared with the air cooling. So in case of air cooling, I will discuss one problem which we try to solve. So we have, in this case, is 8 cells which are in series configurations. So you can see here inlet and outlet is there. This is the whole module. So we have to actually design this module in such a way that the temperature differences between the cells is minimum, and the maximum temperature is also minimum among the cells. And also we have to minimize the volume. Okay, so how do we design? Design means we have to find the optimum value of D1, the spacing between the cells and the water hole. Okay, here also D4 and D3 the same thing, and and the D2. So these are symmetric. First 4 and the last 4 are symmetric. So this is actually a multidisciplinary design optimization problem. So we can define this problem in ANSYS, and also we can solve this problem in ANSYS. So the methodology we try to use, we adopt for solving such problem is we design an air cooling module. Okay, so we can design the air cooling module, which I have shown before, and then we can provide all the necessary models, equations in the module. Okay, so we define the material property, design variable, and heat generation model also. So then we perform the grid independent test and select a suitable scheme. And then maximum temperature differences of the cells, temperature standard deviation, and the volume of the pack module is evaluated. So these are the 3 actually outputs, or we can say the objective, which we try to evaluate. Initially, we do just normal CFD analysis, but then to generate the surrogate models, we need to do the CFD. So hypercube, many samples of CFD analysis using lateral hypercube sampling technique, and then we make models based on this data. Okay, so how we select the surrogate models and we fit on this data to form our models. So what are the models we form? We will form models for each standard deviation one, volume another, and the maximum temperature another model. So there will be 3 models. So we will form the model for each of them, and then we will optimize these models together. Okay, so we will optimize this model together using the multi-objective genetic algorithm, and this is how we select our final the best scheme. So so these are all the necessary equations for the CFD modeling, which we already inbuilt in the CFD in NC's case. And we defined 3 objectives: temperature deviation, temperature standard deviation, and the volume of the pack. So D1, D2, D3, D3, D4, and small v. So small v is actually the air flow rate, and D1, D2, D3, D4 I already mentioned before is this one. So D1, D2, D3, D4. So this kind of analysis we do in the ANSYS, and then we design 3 models. Okay, RSM, response survey methodology, radial basis function, and regime. So we give an input, we get an output, and we fit this. We try to find this function. So FVAR, these are the functions: RSM, RBF, and regime. So now, after we have find the modules, so now we have to define the objectives. Okay, so we can define the objectives, and we can also define the constraints. So in this case, design variables is D1, D2, D3, D4, minimize TD, TST, and volume together simultaneously. And D1, D2, D3, D4 are the constraints. So these are the 3. This is actually a multi-objective design optimization problem. And now we can use genetic algorithm NSGA2 to solve such a problem. So when we use these algorithms, we can find initial design and the optimized design case. You can see here initial design. In this case, we are seeing the quite non-uniform, quite high temperature in this 8-cell pack. And when we use the optimized scheme, and then you can see that the temperature is quite uniformly distributed, and it's in the threshold range below the abnormal range. So this actually proves that optimized scheme can be very useful. Optimized design scheme can be very useful actually to minimize the temperature. Okay, so this scheme is without air cooling. This is with air cooling. Okay. So of course this has to be validated with experiments. And in conclusions, we have temperature difference which decreases 5.3 to 4.0. Volume of the also reduced. So this is what technique I always suggest, that we should try to first design our pack and then simulate it and find the optimal.
Sir, what are the 2 cases shown in each of the scheme, initial and optimized?
What are the
2 cases shown in each of the scheme, initial and optimized? There are 2 pictures shown now for each scheme.
Two cases.
Optimized means with air cooling, and you have 4 pictures now. 4 pictures there.
4 pictures. So this is actually we provide the heat to the model, heat generation model, and we see after, let's say, after 1 hour or 2 hours, what is the battery thermal behavior. Okay, initial scheme means without any charge and discharge. I mean, initial scheme, how is the battery? So this one, this picture will be after, let's say, 1 hour or 2 hours. How is the battery behavior after we have charge and discharge for, let's say, 50 cycles or 60 cycles?
Okay, so these 2 pictures are at different times.
Yeah, different times. Yeah, different times. Yeah. So similarly, we also try to do liquid cooling. It's a similar process. Okay. But in liquid cooling, we have a different design. So we have these cold plates, which are actually sandwiched between the cells. So there will be a cold plate between the 2 cells. Again, the cold plate between the 2 cells. Okay, so this is a schematic diagram for this one. And also we can, here also with the same thing, similar way, we have to find the optimized spacing between the cell and the plate and the wall. So a very similar process, and also the flow rate of the liquid flow rate. So very similar process. We have to also design this this pack in such a way that we are using the minimum space and resulting in the minimum volume of the pack. Very similar. So again, the same process. We design the liquid cooling system and conduct the CFT analysis, evaluate the surrogate models, and then formulate the optimization problem, and then we use the multi-objective genetic algorithm. So very similar way, we actually write the equations and do the necessary modeling, and then we do our necessary predictive estimation for different model, response surface, radial basis, region, and very similar. I mean, I'm just going quickly. So minimize the temperature difference, minimize the temperature standard deviation, pressure drop, total battery pack volume. And similarly, we also try to find the optimized solutions for this, because there can be many solutions. So what are the feasible solutions for our case? So very similar process we follow for liquid cooling also, and we can try to define our optimized scheme, initial scheme, as well as the optimized scheme for our liquid cooling process also. Very similar. So here we can see that the large surface area where we have more high temperature, and here we have seen a relatively lesser. The improvement is not very good here, but that it depends on a lot of conditions, actually, other parameters also, and also the algorithm design. So this is how we have tried to show how we can design the pack with the how we can optimize the pack design using our ANSYS and CFT analysis. So this part has to be validated with experiments, which we have done, but I'm not showing here, which we have done. But we have done for 3S 4P and this 8 cells, but we have not moved to the larger one. So larger one definitely need an industry collaboration or an industry partner to carry out realistic designs. We can achieve efficiency, optimized efficiency of 5.7%, 0.82, and 4.53%. So this is for the liquid cooling. So I will now briefly touch another problem, which is generic framework for recycling of battery pack module. So this is actually the recycling aspect. So this problem, which I was actually working before during my working experience abroad. So because in countries like Japan, Korea, China, or USA, we have a lot of electric cars, electric vehicles in the market, e-bikes also in the market. So they have the companies industry in those countries. They are actually now trying to work on establishing the standards, as well as industry which is fully automated for recycling of battery pack. So you can see that this battery pack, by 2020 or India maybe 2025, we can have up to 250,000 such battery packs in the market whose life has already been over. So how we are going to dispose, or how we are going to recycle such quantity of packs? So this is a very big challenge for us, and how we can do this efficiently, because all the companies are giving packs in their own standard size and own specification. So the standardization is not there also. So that is another question. And how we can disassemble the batteries from each other efficiently and in a timely manner and safely also. So that is also a question. So the basic concept of recycling from battery from the EV is like this. So you have seen this. We can see this EV. We have a pack. We have to discharge. Yes.
In continuation to air cooling and liquid cooling, you have not shown the PCM-based thermal management.
No, we have not. I have not. We have not carried out this in our lab. So So this one I have not shown.
Okay.
Yeah. So this one. So concept of recycling of batteries from EV. So we actually try to. We have this EV with the pack, and we try to discharge first, and then dismantle it, and then we can recover the cells. We have to disconnect the wiring system and everything, and we have to recover the cells. Okay. And now we have to, after we have recovered, let's say 1,000 cells, we have to identify how much energy is remaining in these cells. Okay, how much energy is remaining. So based on that, we can take decision whether we should do chemical recycling, or we should form the new packs, or from this, or we can use this cells for secondary purposes. So this is a challenge there. This part till now industry is manual, is mainly doing manual, because one reason is there is not much quantity of packs in the market. But in next 5 years or 4 years, this problem is going to be a very crucial one, and we will need a very timely mannered, effective and efficient recycling method. So therefore, we try to propose a very basic framework, very qualitative framework, I will say, where we have to use efficient techniques from detection techniques, where we can detect how much is the energy remaining in the battery. Also, we have to find the disassembly sequence, because here we have to disassemble the cells, disconnect the wire. So we need to find how we are going to disassemble and disconnect this whole system in a very timely manner, and also in a safely manner. So for that, we need to have database, data exchange system, and also we may try to use robot-assisted human automatic robot. So this part robots can also play, or machine-to-machine collaboration. So that is why. So I will say roughly this step 6 is more mechanical, and step 6 to step 8 is actually chemical. So this process will have engineers from mechanical as well as chemical background working together to solve such problem. So I will show you a very small experiment which we did before on the battery packs, which we are already there in the market, which were all whose life was already over. So we try to actually do it manually. So I asked my students that, okay, you can collect this battery modules from the market, and you can start dismantle it and start recovering the cells. So this was all done manually, because we want to first of all study what is the existing physical and structural composition in the pack. That is one of the reason. And second, also we want to see how is the cells in this pack whose life has already been over more than 3 years. So how these cells are behaving, are they still having some life or not? So you can see here old and used battery packs, we recover the cells here, and we did some testing on this cells. Okay, so when we did some testing on the cells, we found that these cells, many of the cells still have some life remaining. Not all of them, some of them have cells, so life is still there. I mean, capacity is still very good, and the voltage rating is still going good. Although the life of the pack is not there, but the cells have the life. So you can see here we formed some individual small packs, 3S, 4P, which is used in some other purposes. So this is one of the example of reusability. Okay, so this is also one important concept will be, and in India also, there is a now trend going on how we can reuse the battery packs, because now there will be a lot of e-bikes in the market, and government is pushing for reforms in charging stations and e-vehicles. So there will be definitely how we can reuse the packs whose life has already been over. So that can also play an important role. So these small packs can be used for secondary applications. So we did some testing of these packs also in very adiabatic conditions to see how is the capacity of these 3 packs. So you can see here we are receiving for pack number 3, we are getting a very good amount of capacity behavior. So similar, I think this process actually we have done manually, but I think it can be done in a very more smoother and fashion, and more in a timely manner. So another part I want to discuss is that if we want to do this process in a very timely manner, so we can think of something like robotics or automation systems. So this project is very in kind of immature stage, still in immature stage, but we are working actually to design the initial concept, how we can do this part. So you can see here, if I show you one figure in this figure here, there is a battery module and with the robotic arms. Okay, so we have to this robotic arms will do disassemble, disconnection, disassemble, and grab the cells, and also identify the cells, how much life is remaining. So this robotic arms has to be very intelligently programmed for all this kind of task. Okay, so we have to have object detection system, which is cell detection system, and also coordinate values. So this is all the information processing part which robotic arms has to process and then do the necessary task. So to do this, our students, they actually first decompose the pack and they study all the compositions, because we have to be very careful that the robotic arm which are going to be used on these packs has to be very carefully dismantled and separate the important components like BMS, and the cells also should be very carefully handled, because they can cause any short circuit in electrolyte. This part, which is my students were doing actually for this one, but it's still in immature stage. We did for a very small module, like something like this, but the results we achieved for some of the steps, because we recorded this. This was the manual steps. You can see here. Step number 1 to 13 is done by manually, unscrewing the screw, removal of this. So this is the disassembly sequence. We try to copy this sequence and try to do with the robotic arm, the similar, but we do step 1 to 4, then 5 to 8, something like that. So we are not done it together, okay, because this is still in immature state. So we try to do it one by one, and we try to record the time. Okay, in some cases, some step have higher time, and in some cases, hand time was better. So we are not yet very sure if we can do robotic time, use robots alone, or we have to do combined. But this thing has to be still done. Extensive trials have to be done on this case, because even we are trying to involve the industry in this case, so that that can be done together with the industry. So something that I realize, as my understanding is that it has to be human and machine to machine interaction and human machine collaboration. So this cannot be done by robots alone, but has to be human machine to machine, and human to machine. So this can be a very good futuristic technology that may emerge. So now I'll fourthly discuss about development of AI methods for modeling and control of the module. This was my past problem, which we were actually trying to address. So you can see that we have a prototype of EV where we have 4 modules. So we are trying to power this to the motor, okay, to run our vehicle. So our problem was that we want to know which of the modules we need to charge first on priority basis, and which one have to be which one has to be charged on priority basis first. Okay, because we use these 4 modules together. So during the actual operation of the electric vehicle, the environmental conditions and the factors such as voltage and temperature condition can cause deviations among the modules from its equilibrium state. Therefore, it is necessary to control the state of battery modules. And for this purpose, evaluation and estimation of battery module is a priority to have information on which module. Although there is a BMS there which can do this part, but we are trying to see what are the existing problem in BMS that predict SOC or SOH. And we will try to incorporate our own model. So for this one, we design some experimental setup here, you can see, and then we have to define the rules. So rules means where we switch on the modules for some period of time, we record the voltage, the current, and capacity, and then we again take it rest. So this has to be done in a very controlled way, because we were not allowed to do the field testing. Field collection, we were not allowed. So we do define our own rules. Based on that, we collected the data. Rules means the charging. So we collected around 6,000 samples of data, and we try to connect 6 outputs, which is on-off state. So these outputs actually we define based on the SOC. So if the SOC we see that is below the threshold, then we can define this that switch has to be off. So switch will be on when it is again charged. So these were the small setup we defined. This is the experimental setup we designed for our this battery module. So we have 6 modules here. So now since we collected all the data, necessary data from here, and we try to apply the deep learning technique, which is very famous technique for handling the big data and classifying the switches. So we use this existing technique of deep learning. So to compare our results with the ANN. So this is the deep neural network and the artificial neural network and the experiments. So we compare with the different set of data. So we are using serial number 1, 196, 390. So these are different sets of random samples we use for our cases. So it's not like we are testing it on the same data. We are doing the random test on the different set of subsamples from this 6000. So our purpose was to predict the capacity. So based on that, we can predict SOC as well as the SOH, so which is defined by current capacity upon rated capacity. Okay. So the other part I will discuss is how we design the battery pack module and enclosure for minimization of mass, natural frequency, deformation. So this is more about the mechanical part. I mean, because we also have to make sure that our battery module is not undergoing any resonance or also not undergoing any deformation. So this is all the safety aspect, mechanical safety aspect. Okay. So this is the module and the case we actually built. So this is for the entire pack. This is for the module casing. So we fabricated this from the third party, but we are actually designed this in the MCS itself. Okay. So we always mention that we always have to identify the critical component. We do conceptual design. We apply the necessary design optimization methods, redesign component, and validate and test. So this is actually for any component design and analysis for EV, or it can be for any other system. Okay, so this is a very basic battery pack enclosure design in ANSYS. So we have 12 modules in this case. So this is a very basic one, but we have around 56 parameters in this case, but I have only listed 4. So we do static analysis. Okay, so we do static analysis where we consider aluminum alloy as a material, density, modulus, ratio, everything is given. And what is the objective function is minimize the mass, minimize the frequency, minimize the deformation. So what are the design variables? Design variables here is thicknesses of each of the components. So thickness of this outer enclosure, inside enclosure, and even the modules. So thickness. So these are all the thicknesses: battery case thickness, bottom thickness, wall thickness, module bottom thickness. So this is all the thicknesses and the temperature. So we do the static analysis. We try to find the frequency, the first order frequency. Okay, this is from the model analysis. Sorry. And then we also did the we also propose the 4 methods. Actually, this is basic analysis we do, and this is the deformation analysis. As you can see that the maximum deformation is in the center because the battery weight is acting in the center, the maximum battery weight. So so this is we do based random sampling using LHS, CCD, combined with neural network, regression, and genetic programming with and without uncertainties. So this is all the optimization part after we have got design and we did design analysis. So we use our own genetic programming interface to do this necessary analysis. So we found that these are some design values, optimum values of design variable that can actually result in the improvement in some deformation and frequency as well as the mass. So we try to minimize the maximum deformation in this case, maximize the first order frequency, and minimize the weight. Okay. So this is all the part of the optimization. So before that, we did all this design and analysis. So similar to very similar to what we have done before also for the ANSYS for liquid and air cooling. So here we manufacture some battery module case and the battery pack enclosure. So for our own case. Okay, so we use this tray then in the our real case where we have the prototype. Okay, so this is for the mechanical design part. So of course we also have the liquid cooling before. So other techniques which can be used, we think that we may use topology design because to minimize the material usage that will result in low cost. So you can see here we are using a lot of material in this case. So maybe topology design can be used because topology design optimization is a technique which can optimize the material layout. Okay, we don't have to use all the material, but it can be a material layout. For example, honeycomb structures. Maybe a honeycomb can be shape structures can be appropriate. So this research has to be still done, carried out. Okay. So I will discuss some of the ongoing works where we are actually still trying to do some problems. So topology design optimization of battery electrodes for improved capacity. So once. One. So there is some problem with this slide. Okay, so topology optimization of the silicon anode structures. Okay, so if we use graphite anode, we can see that there is a lithium ion intercalation of 372 milliampere hour per gram. There is a 6 to 10% volume expansion, high intrinsic conductivity. If we use silicon anode, okay, so there can be a rise of 310% volume expansion. Okay, other than this, a lithium intercalation of this, and there could be a problem of low intrinsic conductivity. Okay, the conductivity may become low. So how do we solve this problem when there is large volume expansion and large stress is generated? Okay, so this can actually be either we can develop new materials, okay, for silicon battery, or we can also work on topology optimization approach. Okay, so topology optimization approach, again I mentioned, is that it will try to minimize the material layout within the cell. So for example, if we consider this as an anode, part of an anode, okay, a very part of the anode, our objective is to minimize the volume extension and increase the electrical conductivity. So if this anode part, we can redesign it using the topology optimization. Okay, so the anode may look like this one. It may look like this one. Okay, a part of the anode, it can look like this one after we have achieved the topology optimization. So this part is also very interesting, that because it involves a lot of mathematics in this case and a lot of theoretical models in this case. So this is still ongoing work which we are trying to do. This is an alternative to developing new materials, or an alternative way. Okay. And other part which we are actually trying to do is digital twin for battery pack for EVs, which I will try to do. We are not actually doing this part now, because digital twin actually is a new concept where we actually make a copy of the entire battery pack. Okay, it's like a copy. So we make an entire copy, and that will provide us the information back to the real vehicle in real time. Okay, so all the information such as SOC, SOA, temperature, even forecast the battery conditions in real time back to the vehicle. So this is an integrated multi-physics, multi-scale probabilistic simulation of the vehicle or the system. So digital twin, actually we use this for the very multi-physics and very complex systems. We are not going to use for the simpler system. Okay, so this part is very important for the batteries, because in battery we have electrochemical aspect, we have mechanical aspect, we have chemical aspect, we have electrical aspect, we have material aspect. So the idea is that why not we can form the models from each of the aspect. Let's say electrochemical model, mechanistic model, electrical models, equivalent circuit models. So if we can form this model from each aspect, and we can somehow fuse them or integrate them and calculate those parameters in real time using this all fusion based models of all these different aspects. So that can be kind of a digital twin for the battery, because all these models have their own advantage and disadvantages, all these models. So some of the models are very computationally extensive, like electrochemical, and hard to be computed in real time. So we go for the electrochemical reduced order model. So therefore, digital twin can play a very important role, that we can develop digital twin for a small battery, for a cell, for a battery module, for the battery pack. So to do this, we need to make use of machine learning, Internet of Things, very extensively, and we need to have a very powerful server using cloud computing. So cloud computing, IoT, and machine learning will play a very important role, because this has to be computed very efficiently and effectively in real time. Okay, and this part will be a very multidisciplinary approach for our different branches: mechanical, electrical, chemical. which we are actually working on a very short paper is what are the existing application in battery industry. So in case of battery, we can see that we can do digital twin at the research and design phase. We can do during the manufacturing phase, okay, and also during the operation phase, which is after sales operation. Okay, research design phase, we can collect all the initial data from the cells or the batteries, okay, such as charge discharge profile, thermal profile, and SOCEV voltage profile. During the manufacturing case also, we can collect a lot of data from the manufacturing factory, okay. And then from the operation phase, we can of course collect data for voltage, current, capacity, and develop, design the new BMS. So this is digital twin for every phase can be designed. So what we trying to propose is that why don't we define the digital twin for design, manufacture, operation, and post-operation. So in case of post-operation also, this will be very useful when I talk about the recycling aspect. Okay, so these all can be clubbed to one storage system, cloud storage system, where all the data will be set, okay, from all different phases: research, design, manufacturing, operation, and post-operation. So this is something needs to be done in the, because nowadays currently the research is very disintegrated in my experience. So electrochemical researchers are doing their electrochemical modeling, electrical are doing equivalent circuit modeling, mechanical guys, materials are doing mechanistic modeling. So why don't we have together one cloud storage server where we have all the data completely stored, and we can combine, integrate them, and do this analysis in real time. So this is something which is maybe upcoming one for the research. So in this aspect, we need to design new BMS, also new communication protocols, and new management system. Battery swapping station is also taking very good these days. Encouragement from the government that they are trying to will install the battery swapping station at the oil stations, where we can swap the batteries, and this can actually help in commercialization. So these are some existing things which are going on. And there are, in conclusion, I will say that the lack of digital and physics-based model that is very accurate enough or can be implemented in real time. So these are some parts still lacking, and very, I will again say, interdisciplinary integrated models are still not there. So technologies that are emerging are digital twin, okay, topology optimization for novel electrode design, non-destructive testing methods such as infrared, or we can use optical methods where we can try to get the parameters of the battery in real time, intelligent assembly disassembly methods for recycling. So some emerging techniques are already there that can be explored and research can be done. And then this is might just show you the overall contributions where we have designed our new cooling mechanism, new mechanical pack design. Again, this is a part which we have done some contribution in batteries and battery pack design. So to do this part, we have to go through material phase, SOH analysis phase, battery pack inside design, battery pack enclosure design. So a lot of techniques, lot of methods which are either experimental or numerical or optimization methods has to be used together to solve a particular problem. So yeah, and I also like to declare as some of the PhD positions I have available in my department. So if any one of you are interested to apply for the PhD, please write to me at my email ID. So I will welcome students. Maybe it will be crucial if they feel that this topic is interesting and they meet their background, and they are welcome to apply with their email ID. Okay, so yeah. Dr. Amit? Hello? Hello? Hello. Hello.
We can hear you, sir.
Sir, you are audible, sir.
Hello. Can you hear me?
Dr. Ahkil, yes.
Yes. So I have finished
Sir,
my
done with the talk.
Yeah. Yes.
Okay, so participants, any questions you would like to ask?
Yes, sir.
Yes, please go ahead.
Thank you, Professor, for that
Yes.
beautiful talk. And I have some clarification. Say, if we have to do the simulation of these batteries,
Yes, sir.
is MATLAB platform just enough to do the simulation analysis of these batteries?
MATLAB can do that part also, but it will be mainly focused on equivalent circuit models. For example, Simulink. MATLAB has Simulink, and they have a lot of existing equivalent circuit models for batteries and electric vehicle, lot of already there. So, but it will not be able to do for electrochemical analysis. So, electrochemical analysis, we may go for COMSOL or other software.
COMSOL.
Yes, COMSOL. Yes.
Okay.
MATLAB can do
thermal,
for thermal analysis. I think COMSOL as well as ANSYS both can do. Yeah.
Are they freely downloadable software, or we have to purchase, sir?
I think COMSOL will be available. You can get COMSOL from somewhere. I think in your institute, definitely. And ANSYS also you can get from your institute. Students have these days these softwares which are already there. COMSOL also have battery module inside. They have very well integrated battery module where you can do all electrochemical, EIS, all those analysis.
Thank you, sir.
Yeah, no problem.
Yes, any more questions?
Hello, sir.
Yes.
So, it's regarding actually in your some slide, I don't remember the slide. It is shown that energy density of the cell and the battery module, there is huge variation. I think I could see up to 50% also variation in case of the Tesla.
Yes.
What may be the probable reason for this? Actually, this is our cells are all connected in series or parallel, right? So
Yes.
only the contact resistance or something will be there, no, which is reducing this.
Yes.
Yeah. So then probably all will be getting converted into heat, right? Which is again affecting the safety aspect of the battery. So I think we need to the primary focus should be on reduce this losses, because contact resistance up to 50% is very high, right?
I think that is also one of the very important aspects that you have mentioned, that the contact resistance between the cells, because these are configured in series and parallel. That is also one of the reasons for energy density or the reduction. Yeah.
Okay. And
Yeah.
it's you mentioned about different cooling system, like air cooling
Yes.
as well as liquid cooling also.
Yes.
Yeah. So like probably for automotive, like moving sort of this automobiles, like I think air cooling will be the air cooling or combination will be the best. And for stationary applications, maybe like in enclosed places, we need to go for liquid cooling, right? And one more thing, what will be the type of coolants which will be used, like the cooling system, like it will be like like nano cooling, nano micro systems. What will be, and whether it will be some forced forced circulation sort of thing for cooling?
Yes, sir, there are. It depends on the type of systems we are using. For high discharge, where we are actually going for very high discharge rates, that kind of system we use liquid cooling, and in also liquid cooling we can have the forced cooling systems also. So it depends on the type of system actually. Very much depend on it. We have used actually nanofluids also, other than water as the coolant. We have also tried to use nanofluids. Okay, for our case, where we have tried to see if nanofluids can be important. So that term has to be investigated actually for each of the system.
Okay.
Yeah, nanofluids in place of water. There are a lot of that have been investigated actually, depending on the different systems.
Okay, sir. Thank you.
Yeah.
Any more questions that participants would like to ask? So if not, I think we'll conclude. Thank you, Dr. Ahkil. It was very nice of you that you came and then you delivered a talk on battery modules, and now at least all of us have got some understanding about how battery packs work and how they can be modeled, what are different issues that can be resolved or can be looked into. Thank you so very much for coming.
Yeah, thank you, Dr. Amit. Thank you very much.
Thank you so much. Participants will have now break. We will come back with the third session of that is the last session of the day at 2:30 p.m. Thank you very much.
Thank you, sir.